Welcome back, everybody. Today we're going to talk about circuit branching. We're going to cover a few things around circuits in parallel, circuits in series, combinatorial circuits, and something that we use called Thevenins to find out what a reading should be when we're taking a reading.
Nice. Let's do it.
Yeah, exciting stuff. So, um, when we're talking about
DC circuit.
yeah, so we're going to do a little bit of stuff that should be review for everybody here. A basic circuit contains a power source and a load. A series circuit is going to contain multiple loads one after another so that the current has to flow through each load to get to the next, a load being a resistance. So here's a quick diagram for that. Here you can see we've got our uh, battery over here. Everything, all the current that goes through load one also goes through load two, also goes through load three. Pretty
Yeah.
simple. You
And that's
should,
why current is constant throughout the circuit, right?
yeah, like the same amount of current is going through each load, even though each load is really only concerned would only draw on its own a portion of that. Um, the current through each of these components, as we said, is the same. The voltage across each current is the sum of the voltages across each component. Essentially, voltage
And
goes,
that's what and that's what we call voltage drop, right?
that's what we call voltage drop, right? So the voltage drop across each component in a series circuit is going to vary based upon the total voltage of that circuit and the total resistance of that circuit. And so we have to figure that out proportionately. And we'll go through some exercises in another video that'll show you exactly how we do those calculations.
And you guys remember some of this that we went through with the Radio Shack trainers in IMO. So we worked on some of this, and hopefully
And you'll be
shake the
gaining some,
cobwebs off. Yeah.
you'll be gaining some more reps on this and taking it a little deeper here using Thevenin's on those same trainers. So um, yeah. So none of this should be fairly like none of this should be totally brand new to you. It is stuff that we did cover in IMO. Uh, we'll be carrying it on and we'll be deepening our understanding in that. Um, a circuit in parallel is something that is connected along multiple paths. So something is in parallel uh, when the same voltage is applied to each component. Um, the voltages across each component is the same, but the current is the sum of the currents through each component. So it's
Yeah.
kind
So
of,
we just flip things around, right? So now voltage is constant in parallel,
yeah,
and current is not.
yeah. So if we look at a visual example of three loads in parallel here, each of these is getting whatever the voltage is here of our power supply. So we've got, if this is 9 volts, each of these components is getting 9 volts, and the voltage drop across this is going to be from 9 volts to 0 volts. The current going through this individual component is going to be based upon Ohm's law for this one component and that voltage because it's going to differ. The current going through each one is going to be different because some of the electrons are going to go through this pathway and some of the electrons are going to go through this pathway and other electrons are going to go through this pathway. So it generates a different current on each component.
Yeah. And as you add load to it, in a parallel circuit, current will increase.
Absolutely. Absolutely. And our total current, what's going through these wires here and here, are determined by summing all of these currents up. Um,
So we just mentioned this, right?
yeah, this is just an
DC circuits.
explanation of
Yep.
what we talked about on the previous slide there. The current flow, like where we look at the power supply, is usually greater than in parallel circuits because we're adding up all of these currents, and so they'll oftentimes parallel circuits will drain a battery faster. Um,
Yeah, a lot
which
more load on it.
which makes sense. You're putting more light bulbs on it. You know. Um,
Total resistance,
total
pretty
resistance.
simple, right?
We
You
just
know,
add
it's
all of
equal
them
to the
up.
sum of, yep, equal to the sum of them.
Yeah,
So,
and that works in series. However, if we are dealing with resistance in parallel, um, we use 1 over R total equals 1 over R1 plus 1 over R2, 1 over R3, et cetera, et cetera. The total, like for this reason, because we're running this inverse function on things, the total resistance will always be less than the value of the smallest resistance,
hmm
which is something that you can use as a smell test on whether or not you've done things right. If you've run this calculation and what you come up with for R total is more than one of those resistor
lowest value.
values in there,
Yep.
you're you're uh, you're doing something wrong.
Something wrong with your calculations.
Yeah. Um, so keep that in mind as you're going through and doing some of the math behind these sample problems. So what happens though is circuits can be complex. What is the total resistance here?
And that's a head scratcher on this one.
Well, first of all, we don't know what all the resistances are. Do we even know what's in series and what's in parallel in this circuit? Not really.
No, I mean that's
It
that's a
depends,
tough one.
and this is the thing. A lot of this depends on the perspective of where we're testing, and that's what Thevenin gets into. Um, so if we put our probes for our ohm meter, we like you don't want it connected to a battery when you're testing resistance. That's not how you do it. You disconnect power. Um, but if we touch A and B on this one with our two probes from our multimeter and are testing resistance, what's in parallel and what's in series?
Tough to tell.
Yeah, you kind of have to do a little bit of spatial acrobatics, right? And if you touch A and B, actually what happens is R1 is in parallel with the combination of R2, R3, and R4, right? You've got this one, R1 in parallel with R2, R3, and R4 in series with one another. So that means that you would add up R1, R2, and R3, and then you would do the 1 over what you get there and 1 over R1 to get the total resistance that you're going to read. But it would be different if we were measuring between point A and point D. If we were measuring between point A and point D, we would have R1 and R2 in series. We would have R3 and R4 in series. And these two branches would be in parallel with each other. So we would add up R1 and R2, we would add up R3 and R4, and then we would take 1 over those totals, take the inverse of that, and we would have our total resistance. So we'll do some examples around this when we get into Thevenin's, because Thevenin's deals with exactly this. Thevenin was, we'll get into that in one more slide here. I promise we're getting there. But it uses this spatial logic. So when you're dealing with circuit analysis, you need to determine this perspective. Where are you measuring, right? Where in the circuit are you measuring? And then from that perspective is where we determine what is in series and what is in parallel. Then we find the total resistance. And then we find the voltage drops using proportion to the total resistance. And we use Ohm's law to find the current. And then we have all of our answers. So this is kind of the workflow that we're going to be going through. And when we,
Yeah, very important steps to follow. You will get confused or you will get different readings if you don't go through this workflow
Yeah.
properly, and sometimes it's good to put different brains together, and if you can't figure it out, start working together and come to a consensus, and then start taking some values from that, and then
Yeah.
making your calculations.
Now this workflow is what we'll be doing when we're doing circuit analysis to find what Thevenin's voltage should be, what Thevenin's resistance should be, and we'll do that in another video for you that will actually physically demonstrate that by measuring actual resistors under a load for you at a later date.
Sounds like a plan.
But before we get to that, I just want to tee up this ball. I want to give us what Thevenin theorem is. So Thevenin's theorem is a way to analyze more complex circuit, and it's basically a trick that treats your circuit as a black box, and there's 2 points that you're measuring from. So essentially, it's exactly that. It's the first step. We're identifying this perspective. We're measuring those two things. And Thevenin's voltage and Thevenin's resistance are exactly what you measure when you put your multimeter up to it.
Yeah, essentially it's making analyzing the circuit easier. Yeah,
Yeah,
especially when you have when you want to like review or study the effect of maybe how the loads are changing in that circuit.
yeah. And so that black box contains one voltage and one resistance. It's what we measure. Now, uh, what that means is that all of those things we boil down to figure out what the total resistances are and the total voltage drops are uh, across those 2 points that we've chosen. Um, Now uh, we can use circuit analysis with the full schematic. If we have that available to us, we can use circuit analysis to derive what that equivalent circuit is and find out what our reading should be, right? Because
Hmm.
if you're taking it and you get a voltage, or you take it and you get a resistance, is that right? Is that what it should be? Well, you won't know unless you've done the circuit analysis to identify what the equivalent circuit actually would be, given the resistances on that circuit. So what we do is we use circuit analysis to find the equivalent circuit. And this is really useful if you want to place a load between terminals, but even more useful to us as technicians is uh, is knowing, like, this is what it should read. Like, this is the reading that I should get when I touch these two terminals. I'm
Hmm.
getting something different. Therefore, there's something wrong that I need to investigate.
Yeah, and also, as you mentioned, Jason, if you do want to add a load into that circuit,
Yeah,
understanding what the effects are on the rest of the circuit when
it
you add that
is
load to it.
super important. Yeah, if you're modifying things, if you need to put in a pull-up resistor or a pull-down resistor into something, like, this is all going to be part of that.
And what page did you say this was on in their
Oh
book?
yeah, there's a good example. Um, it's page 77 in your book, Practical Electronics for Inventors. Page 77, there's a good primer on this. If I can point this at the camera correctly, I'm not pointing at the screen. I'm pointing at the camera. So this shows you how you construct these, and we're going to kind of we'll give you one more bullet point slide, but then a lot of this you may want to look at this before you come into class on page 77 of your book, just to prime yourself and be super ready to go for when we do that demonstration video. So there's two measurements. There's Thevenin's voltage and Thevenin's resistance. These are the readings that we can get out of that black volts. Thevenin's voltage is the voltage across the two terminals with the power on, right? With our normal power supply attached to it. Uh, the resistance is Thevenin's resistance, or Rthev, and this is the resistance across those two terminals, but we remove the battery, we remove the power sources, and then we short the wires between those power sources. So we'll show you that. And as soon as we do that, now all of a sudden, a lot of times things will change as to what's in series and what's in parallel from what VTheb has on it. But then it works out when we actually measure it. So that's one of those things that you've got to used to. I mean, from there we can apply Ohm's law and we can find the current flow across a load placed between the 2 points, and this would be exactly what you would do if you're like trying to put in a pull up resistor or a pull down resistor into a circuit. You want to be sure that you kind of know how it's going to make the circuit behave.
Yeah, and go
Uh,
back through and always, double check your calculations as well.
yeah,
Um, something doesn't seem right, just run the calculations again, have somebody else look at it and see, does this make sense? Does this look right? This is what I'm finding. Because, it's hard to operate in a vacuum and then, carry on with what you're doing, thinking that you're doing everything correct. And, you might not have any doubts, and sometimes it's just good to have somebody double check it anyway. But if you do have a doubt, for sure have somebody else look at it and just kind of cross check what you're kind of the path you're going down and make sure your calculations are correct because we're human, we make mistakes. If we're not you know uh, writing down these calculations correctly, or maybe we missed a value, it's easy to get derailed by that, and then now you got a bunch of work you did for nothing. You got to go back
yeah.
and redo some of that.
And doing this stuff on paper is kind of important. Like this will help you a lot, and it'll make it so that you don't tear something apart that you don't need to tear apart.
Hmm.
I remember working on an oven at one point, a big, big composites oven, and one of the one of the elements was not working. Right? There was something wrong with it. It wasn't reaching temperature, and so I was poking around to figure that out. And like all of the connections that are hidden away behind panels in an oven that are insulated that you don't want to get into with the insulation. It's
Yeah.
if you know what you're doing here and can read a schematic, it becomes as simple as jumping a couple of wires and turning the power off and then turning the power on, and then you'll be able to get exactly what you should be reading across all of these different elements. Um, and you'll see, like, this is what the circuit says I should be reading. This is what I am reading. So therefore, the problem is this. And I don't need to tear it apart other than when I need to swap a part out. And
Yeah.
that can be tearing down a lot less as a result of me doing that work on paper. Because yeah, I could take each and every heating element out of the oven and
And test it and
individually
do all
test
that.
its resistance. Um,
Yeah, the amount of time you're spending on that is
it's
exponentially
just
higher
huge when you're
than just
talking
going
about
through
a
it.
giant oven that you can crawl inside.
Yeah.
Um, so yeah, that's why we're teaching this. That's where you'll use it. It's a great way to make use of the documentation of schematics when you have them, and why you should make schematics of things that you don't have schematics of.
Yeah.
Because if you're tearing something down, you might as well make a schematic of it, because then you likely
Yeah.
won't have to ever tear it down to the same level ever again.
Yeah. Yeah, you're just documenting that whole process, right? And then that way you're it'll help you put things back together, but also uh, you know, you have some documentation from that work you put in. I
Yeah,
mean, when you end up with no documentation, you just did all this work, and it just goes with anything you take apart, that you don't understand fully. You're more than likely going to make a mistake putting everything back together, and just do yourself a favor, document schematics. We've done some of that already in IMO. Just continue on that practice, and it's just you continue to get better at it. Just it's good to keep practicing with that particular skill because in the industry, definitely you will end up using it.
yeah. So that's all we've got for you for this video. Keep posted. In the future, we're going to publish that the video on our on how we apply this. You know, just showing examples of us working with a multimeter and a breadboard and doing these calculations on the board. So that'll show you a little bit about the workflow that we just talked about here. Um, and yeah, we'll see you in the next video.
All right.
Adios.
Adios.